Yeah, welcome. We are again having another question, which is from paper 1 in the section of electrodynamics. We are having this 14-mark question. Hopefully, while we are engaging with this question, you will learn some few things. The statement reads that the diagram below is a simplified representation of an AC generator. The coil is rotated in a clockwise direction in a magnetic field. 9.1, you can see the structure there. 9.1, they say write down the name of component X. You can see the component X is pointing at the rings. These are the slip rings. So our first answer will be the slip rings. 9.2, they say write down the function of Y. Y is pointing at carbon brushes. The function of the carbon brushes is to maintain electrical contact with the external circuit. Circuit with the coil. Maintain electrical contact between the external circuit and with the coil. With the external circuit and the coil. Okay, you can just write and the coil, or just to connect the internal and external circuit. So you can use your English there. And then the continue. Yes. Use the relevant principle to explain why an EMF is induced in the coil when the coil is rotated in the magnetic field. We're going to use Faraday's law here. According to Faraday's law, the induced EMF is defined by this, the phi and this. Now, using this, and in generators, we know the principle is electromagnetic induction. That is the principle that is used in generators. According to this, therefore, the EMF is induced. EMF is induced if there is change in magnetic flux linkage. In this case with the coil. Now, the magnetic flux linkage, if you don't know, it's normally this. When multiply the number of coil by the phi, this is what you call magnetic flux linkage. Okay, thanks. Number 9.4. The coil rotates clockwise from the position shown in the diagram. In which direction will the current be induced in segment PQ? So we know in simple terms, when coming to generators, if north is on the left and south on the right, then the generator will follow. If the coil is going clockwise, the generator will also, if the current is flowing clockwise, the coil will also rotate clockwise. If the coil is rotating clockwise, the current will also flow clockwise. So in this case, if it was a motor, then we know that now motor oppose. If the coil is rotating clockwise, the current will rotate anti-clockwise in the case of the motor, which is the motor effect. So this one is just electromagnetic induction. Therefore, the coil is rotating clockwise, then the current will move from P to Q. Therefore, our answer will be from P to Q. 9.5. Now we are given a diagram here. The output, which is the maximum, a voltage versus time graph below was obtained for the above generator. And now the output voltage is generated at a frequency of 50 Hertz. And that one can also tell us about the period or the time taken to complete one wave. Calculate the time t indicated in the graph above. Then we can find the period. The period up to here is a full wave. Then it means that now our period, which is t, will be the same as 1 over frequency, which is 1 over 50. Therefore, it's 0.02 seconds. If from here to here is 0.02, therefore t will be 0.03 seconds. The last calculation in this question now is question number 9.6. They say the generator is now connected to an appliance with the resistance of 100 ohm. Calculate the energy dissipated when the appliance is in operation for 1 minute. Energy dissipated in 1 minute. Now what we need from the formula sheet, we've got various formulas, but in this case we are given, remember, the maximum voltage. We don't work with maximum, we work with the VRMS, main in the formulas. Now we have to convert this one to VRMS before we can use the resistance here. Then that's our first task. Convert, change the output to VRMS. So the output is in Vmax. Therefore, VRMS equals to Vmax over root 2. Therefore, this will be 311 over root 2, which is the same as 219.91 volts. That is the VRMS voltage that we can use. Now, with the VRMS and the resistance, we can calculate now the energy dissipation there. Energy dissipation per minute is the same as what we call is the W. Now we can just use energy dissipation, which will be W equals to, we've got V and R, then we can use V squared over R delta T. This will be the same as V is 219.91 all squared multiplied by 1 minute is 60 seconds, which divide by the R is 100. Then our answer will be 229,016.24 joules. This will be the answer that you obtain. You can find this in many ways. Some people can go for current as well. From the VRMS, you can use the Ohm's law to find the current, and with the current you can also use the formula with, remember, this one can be this, or can be VIT, or can be also I squared RT. Yeah, so if you use any of this, we have to find the current first, then you can use. So otherwise is one of the sections that is having many options, but the easiest one will be going for the first VRMS. After VRMS, then you just use this formula. V and R is there, then you can use this to find the energy. You get all the 5 marks here. Thanks a lot. Until the next session, hopefully out of this one you have seen now what we call the flash linkage, and also how to explain the electromagnetic induction a moving coil in a magnetic field will induce electricity, and that moving coil is due to what we call magnetic flux linkage, which is the multiplication of the number of turns and the phi, which is the field which is cutting across the cross section of the conductor in that case. So until next time, thank you.